Your BFS solution works, but it secretly repeats the same work thousands of times.
Hi everyone and welcome back. Today we are solving the leetcode problem, Jump Game number 7. We are given as binary string and a minimum jump and a maximum jump. We start at index 0 and from every position we can jump anywhere between minimum jump and the maximum jump. But we can only land on a character that contains 0. Our goal is to reach the last element. So now most people will immediately think about breadth first search. Why? Because we are moving from one state and we need to explore all the available next states and so on and so forth. And honestly, this is the correct idea. So let's first understand the basic breadth first search solution. We start first, let's say, we have our queue, let's name it Q, and first we will push the first index, which is 0, into the queue. Then for every position, we will try all possible jumps, which means if the current position is 0, we need to try all possible jumps from 0 plus minimum jump till 0 plus maximum jump. And for each of these positions or destinations, we need to check if this destination contains 0. And if yes, we push that new or next destination to our queue. And so on, we start exploring this new position until we landed on the last position of the string. But there is a huge problem here. We keep scanning the same ranges again and again and again. For example, imagine one node is scanned from index 10 to 100. Then the next node scan will be from 11 to 101. And the next scan will be from 12 to 102. Can you understand the issue here? Most of the work repeated. If you didn't get it, let's make an example. Let's say we have array that is all zeros. So if we started here and let's for example make the minimum jump equal 2 and the maximum jump equal 5. So if we started here, we will scan this range from 2, 3, 4, 5 because we scan from I plus 2 till I plus 5. And then here we already scanned all of these elements in the last scan. And then in the next scan, if we are at 2, we will scan again these elements. Of course, if the range from the minimum jump to the maximum jump is bigger than 3, the repeated processing will be much higher than that. So, as I said, most of the work is repeated, and that is why the native breadth first search gets time limited exceeded. So how we do optimize this? The key idea is never scan the same index twice. It's the same like in the normal breadth first search when you define the visited array. Here also we need to never scan the same index twice. And we can achieve this using one variable. Let's name it, for example, farthest. And this variable will store the farthest index we have already processed. So now watch carefully. When we process a new node, instead of starting from the current index plus minimum jump, we start from the maximum between the current element plus minimum jump or the farthest plus 2. So if we are in the current index, we are processing the current index. Next, we will process the maximum between the current index plus the minimum jump or furthest plus 1, because this is the last index we have processed in the previous iteration or previous processing. So this is completely removes overlapping work. Every index is processed only once, and that will make the time complexity drop to O of n. So let's now go through the optimized code. So first, I'll define variable n to get the string length, and I'll do a first check to make sure that, let's check first the constraints. Okay, we need this check. The check is we check that the last element of the string not equal 0. So in this case, we can't jump to this base. So we will return false immediately. After that, we will define our queue of integer. Let's name it q, and we will push the first index to our queue. Also, we shouldn't forget to define our variable furthest and initialize it to 0. And then we process our queue. So check our queue if our queue is not empty. In this case, we will get the current index, which is the front element of the queue, and then we book our queue. The same steps as any normal breadth first search. And in this case, we check if we have already reached the last element. So if the current equal in -1, then we already in the last element of the string, then we return true. Otherwise, we need to check all the valid destination by defining, let's for readability define stored element, which is the maximum between the current element plus minimum jump, or the farthest plus 1, because farthest is the last element processed in the previous iteration. So we need to check the element next to farthest. So we add the plus 1. And we define variable end, which is the end of the range. That is from the minimum between the current plus maximum jump. Yes. And n -1, because we don't need to go beyond the boundary of the string. And then we iterate over this range for I equal stored. and I is less than or equal to the n and I plus plus. And here we check if s of I equal the factor 0. So this is a valid position, and in this case we push our new destination or index to our queue. And after that we set our furthest element to the end, because this is the last element to process. And if we continue processing all the elements in the queue and we can't reach the last element, we return false. So let's run it to make sure I don't have any. Already have, yes, missing semi-colon here. Let's run it again. It give us false here. I must have written something wrong. We need to check that. Character 0, not 0. Yes, and here we go. Let's submit it. And that's it for today's solution. And as you can see, the entire optimization is just a single variable that leads to a massive performance improvement. This is actually a very common interview technique. Whenever you see press first search plus repeated range scanning, try tracking processed boundaries. It often converts quadratic solution into linear ones. And that's it for this problem. If this explanation helped you understand the optimization, don't forget to like and subscribe to the channel, and see you in next video. Bye.